You are watching Chapter 5, a model for a detached ampulla. First, let's look at the video of a contracting detached ampulla seen early in Chapter 2. We see bulges move from left to right along the top of the ampulla, while white blood cells in the middle slosh back and forth. A 3D color plot of the profile of this ampulla, seen early in Chapter 3, also showed a wave crest moving along the ampulla. This graph of the times of the contraction peaks has 4 lines, one for each ampulla quarter. Each line plots the peak number on the horizontal axis versus time on the vertical axis. The average time between peaks on each line is 65 seconds, the period of contraction. However, the lines are shifted from each other by 17 seconds, since it takes a peak 1/4 of the total period to move to the next segment. The phase, a hidden variable, is central to our model. Any system, mechanical or chemical, that exhibits a regular oscillating behavior can be thought of as a virtual wheel or arm that turns around at a constant angular speed. We usually don't see the turning arm directly, but rather the projection or a shadow of that arm on a line. In Chapter 4, I animated a phase portrait of a contracting ampulla in a mathematical model. The phase, the growing tip of the line, was seen to go round and round in a circle when the ampulla was contracting in a regular way. That line is the curved black arrow in the 2 cells of this diagram. The phase is the angle between the tip of that black arrow and the horizontal. In this diagram, it's the angle of the red arrow to the horizon. The phase tells us both the size of the cell and whether it is growing or shrinking. The central premise of this model is that oscillating cells that are attached to each other tend to acquire equal phases, or at least are pulled towards phases as equal as possible if there are other constraints. A major constraint in our system is that the volume of the ampulla must remain constant. The cell length is proportional to the sine of the total phase angle. The total phase is the angular frequency, the Greek omega, times time, plus a phase offset, the Greek phi. In our case, the angular frequency is constant, and time, the clock, increases at a constant rate. It waits for no man. It is the phase offset that our model has to generate. Phase is an angle, often measured in degrees. However, mathematicians, scientists, and many engineers measure angles in radians instead. 1 full circle, or 360 degrees, is 2 pi radians, about 6.3. In our graphs, the phase will typically go from minus 3.15 to plus 3.15 radians. In these units, the angular frequency is expressed in radians per second. Here we see one cross-section of an ampulla when the cells are long in the radial direction and cell-cell contact is large, and an expanded ampulla when the cells are thin and cell-cell contact is small. In our model, an ampulla is considered a stack of rings like these. Our model has a simplified and exaggerated structure. Here the cells are shown as rectangular in shape, but that's just for ease of drawing. Building the ampulla from rings expresses the fact that cells forming a ring around the ampulla push or pull directly on the other cells of that ring. The cells of one ring interact with cells of neighbor rings, but it's a dragging force, not compression or stretch. Consider ring 3. It is pulled up by rings 2 and 4, and rings 2 and 4 are pulled down by ring 3. But ring 2 is being pulled down by ring 1. Ring 4 is being pulled down by ring 5. To justify using neighboring rings to predict the motion of ring 3, it might help to consider that we are predicting the motion over 1 second time steps. During that second, rings 2 and 4 will have moved down more because of rings 1 and 5 than if rings 1 and 5 had been above rings 2 and 4. Can we create a method to express the effects that the several rings on each of ring 3 exert their effects? This is actually a common type of problem, and a common solution is to multiply each of the rings around 3 with a curve that becomes smaller the further we are from 3. Then sum all the combinations. This curve is called a kernel. The Gaussian curve has desirable properties for this job, and the procedure for multiplying neighbors by a Gaussian and summing is built into many software collections, like Mathematica, the one I use, where it is called a Gaussian filter. In the next section, we will try this and find that it is remarkably effective. In the following few sections, we will plot phases of rings on the vertical axis, since our ampulla is made of a stack of rings, and the phases are the most revealing parameters to follow. We know that a good model will maintain a traveling wave down the ampulla, because a real single ampulla does that. But we will test our model with an extreme challenge and start with the rings having completely random phases. This is a random set of phases. The sharp peaks are quickly smoothed down, and then gradually the curves become a smooth line, increasing continually from minus pi to plus pi, minus 3.1 to plus 3.1, along the ampulla. But we want to see the actual wave, not the phases. So for each ring, we calculate cell lengths using the formula in the previous section. Now we let time increase smoothly, causing the omega t term to also increase smoothly. Each ring moves through successive cycles of a sine wave, but with different phase offsets, and we thus have this traveling sine wave. To me, conversion of rings oscillating with random phases to a smooth traveling wave in these plots is magic. Of course, it's not magic, but just the repeated application of simple code on the phases of the rings. Here are the 3 steps. Step 1 replaces the phases with their moving average. This smooths the profile of phases towards a straight line, sloping either up or down. The direction is determined by the initial random set in some way we won't investigate here. Steps 2 and 3 just normalize the phases to conditions we set in the beginning. The first step drags neighboring rings to a common line. The second step expresses the fixed volume of the ampulla. The third step is just the convention that phases have a minimum value of minus pi and a maximum value of plus pi. Here I have written these steps in Mathematica code. Sm and S smooth are constants that specify the width of the Gaussian kernel and the number of times the do loop executes. Ring P is the list of ring phases. A list is the term used in Mathematica for an array. Lists can be used as simple variables by mathematical functions. While the ampulla walls must be the major link between parts of the ampulla in the creation of a traveling wave, the situation for a detached pair of ampulla is quite different. In most cases, The tube connecting the two ampulla is long and irregular in shape. It doesn't seem possible that a coherent signal could be transmitted along such a structure. Blood pressure must be the major or only time-dependent variable that synchronizes the two ampulla as they beat exactly out of phase, and must also synchronize the cells within each ampulla. A traveling wave and a tunicate blood vessel might seem extremely esoteric, not relevant to familiar systems. However, animal embryos form a hollow structure, the blastocyst, early in their development. The interior, the blastocoel, is lined with epithelial cells and is filled with fluid. Sound familiar? Embryonic development consists of cell division forming cell sheets, tubes, and spheres, which develop complex three-dimensional structures through differential cell growth and cell movement. About a decade ago, it was found that cells in epithelial sheets that are changing shape undergo contractions with periods around 60 seconds, just like our ampulla. It is believed these contractions, breaking and reforming cell-cell attachments, facilitate morphogenesis. There is a huge literature on this subject. I cite just one paper that could get you started. Happy reading. It's June 2024. The sun is out, water warm, and tunicate colonies should be easy to find. I'm going down to the dock to harvest some and do some more experiments. I leave with you an index of this and the previous 4 chapters. Gunther Stent used to say at the end of his lectures, "As the sun sets in the west, we say aloha to our friends." We miss you, Gunther.